Hi, welcome back. In this video, we're going to talk about special segments in a circle. So this is going to look very similar to our last topic, 10.6, which was secants, tangents, and angle measures. The pictures will look very similar, but for the last one, we were looking for the degree or the angle. For this one, we're not interested in those things at all. We're looking for the length of a segment, okay? So the pictures will look very similar, but we're now looking for a distance or a length, as opposed to before when we were looking for the angle it created. All right, so let's begin. Here we have two secants. If I extend those lines, we have two secants because the line crosses the circle twice, right? Like here in this scenario, we have it's crossing here and here. This line AC intersects it twice. ED intersects it twice as well. These chords, because they are intersecting inside, these smaller chords within, we're going to call those chord segments. And the way we're going to find the length of the relationship between them is actually we're going to take the chord segment, so like AB, and we're going to multiply it by the remainder portion, BC. The product of those two, I'll write the formula here on the side. The product of AB times BC will equal the product of the other two. So we're going to say EB times BD. So a part of the chord times the remainder of that chord will equal the product of the other two. And this happens whenever we're intersecting. I'll call this EB times BD. This is going to happen whenever the chords or the secants intersect inside the circle. As in our last video, we can intersect inside the circle, we can intersect on the circle or outside the circle, right? And we'll have different scenarios. We'll do something very similar here. The two chords are intersecting somewhere on the inside, and it's not in the center of the circle. So when they intersect, we take the lengths and we multiply them. So let's check this out. Here we have, in our first scenario, we're going to try to find the value of x. So I'm going to take this first piece, x times the remainder amount times 10. X times 10 is 10x. That should equal the other portion. I'll do this in pink. 5 times the remainder portion, 12. And that's pretty much it. I simplify, solve for x. 10 times x is just 10x, and 5 times 12 is 60. Divide both by 10, and I get x equals 6. The length here would be 6. In this next circle, as you can see in the bottom right, we have a bit more of a complex things because we have a lot of variables and no numbers, or a little bit less view of numbers. But with the problem is set up the same. We're going to take a portion of the chord, x plus 10, times the remainder. So x times x plus 10 should equal x plus 1 times x plus 8. We're multiplying a piece times the other piece and a piece times the other piece. And now here we basically have a bit of multiplying. X times x is x squared. X times 10 is positive 10x. Over here we can multiply through box method, or, right, you can set up a box method if you like. You can do x plus 1 and x plus 8. Or you can do FOIL, x times x is equal to x squared. X times 8 is positive 8x. 1 times x is 1x. And 1 times 8 is 8. Either way, you'll end up getting the same thing. Right here on the right, I can do x times x is x squared. X times 8 is 8x. The bottom, x times 1 is 1x. And then 1 times 8 is 8. And then you're just basically adding all the values up. That's how we get here. So we have x squared plus 10x equals combined like terms, x squared, these two are like terms, plus 9x plus 8. This is basically a quadratic. I want to combine like terms and solve for x. When I subtract x squared, though, notice how it cancels out, and we're just left with 10x. 10x equals 9x plus 8. I subtract 9x on both sides. X equals 8. If I wanted to find a particular length, I would just be able to plug in the 8 into whichever segment I'm interested in. But for now, we're just solving for x. Notice how in this scenario, we're going to be talking about segments that intersect outside of the circle. So here I have secants, two secants that intersect on the outside, and they form an angle. So we have a general scenario here. The way we're going to do the setup is we're going to say the portion of the outside, the smaller piece, multiplied by the entire length will equal this smaller piece multiplied by the entire length, the entire distance. Okay? So here's the setup. We have AB times the entire piece, AC, should equal the small piece on the outside, AD, times the entire length, AE. You can put this equation in words, or you can use these symbols, right? But this piece times everything, this piece times everything. So let's try the example. I have the length on the outside, which is 8. I have 8 times the full length. The full length from here to here, it's x plus 8. We're going to add the two lengths together. That will equal the length on the outside, which is 6, times the full length, which is 10 plus 6, and we get 16. And now we just do, once we have the problem set up, we do some basic algebra. 8 times x is 8x, 8 times 8 is 64, and then 6 times 16 is 96. To solve for x, we isolate the variable, move the 64 over, 8x equals 96 minus 64, and we get 32. Divide both by 8, and we get x equals 4. If we wanted to find a particular length, we would just plug this value back in for x, but right now we're just solving for x. And this next one on the right, very similarly, right? Let's label this with some color. The outside length times the full distance. So the outside length is just x. The full distance from R to U is x plus 9. That'll equal the small length, 4, times the full distance. And the full length from here to here is 4 plus 5, which is 9. X times x is x squared. X times 9 is positive 9x. 4 times the full length is 36. This quadratic, I cannot isolate the variable as we did before, so I'm going to move everything to one side. Subtract 36 on both sides. X squared plus 9x minus 36 equals 0. I now know that I'm going to have two possible x values, right? I'm going to factor. You can use the ACB method. I'm going to do my approach here. I'm going to break it into columns. X times x gives you x squared. To get 36, I can do 6 times 6, 3 times 12, 4 times 9. There's several options here. I want the combination that adds up to 9. And I'm going to do 3 times 12. Since this has to be a negative 36, I'm going to make it a negative 3. Notice how when I cross multiply, 12 times x is 12x. Negative 3 times x is negative 3x. This actually does add up to 9. Hopefully by now we'll feel comfortable factoring. And this column in the middle is just to check our work, right? 12x minus 3x is 9x. So my factors are the numbers horizontally, which is x minus 3 and x plus 12. I'm still solving for x, so I set them separately equal to 0. I have x minus 3 equals 0, and x plus 12 equals 0. When I move things over, I get x equals positive 3, and when I move the 12 over, I get x equals negative 12. Now, since x here is a distance, I'll put this in red. Since x represents a length, when I plug this in here, x equals 3 does work, but negative 12 will not work because we cannot have a negative distance. So we would have x equals 3 as our solution. So now let's talk about tangents. What happens if they intersect, but now we have a tangent and a secant, right? In the previous example, we multiplied the outside piece times the full length. Since here we only have the outside piece, and the outside piece actually is the full length, we're going to multiply it by itself. So we got jk times jk equals the other segment, the small outside piece, jl, times the full length, jm. So, in our previous scenario, we did outside piece times the full amount. Since in this scenario, the tangent line is the full amount, the outside piece is the full amount, we just multiply it by itself. So this is technically the same formula. The outside times the whole equals the outside times the whole length. So let's try some examples. The outside piece is x times the full length from here to here is just x plus 7. On the other side, we're going to have the outside piece, which is 8, multiplied by the full length, which is 8. Outside times the whole equals outside times the whole. And now that it's set up, we can solve. X times x becomes x squared. X times 7 is positive 7x. And then 8 times 8 is 64. This is another quadratic scenario. I'm going to move the 64 over. X squared plus 7x minus 64 equals 0. To multiply to get 64, I have several scenarios, right? Several factors. 8 times 8 is 64. 32 times 2 is 64. You can also do for 64, 64 you can say divided by 4. That's 16, so you could do 4 times 16. What else do we have? As you notice here, we want to figure out which one's going to add up to 7x. 8 plus 8 does not give us 7. 32 and 2 does not give us 7. 4 and 16, when we subtract, we get 12. Let's try another combination. I don't think I can find another set of factors for this one. Now, what that means is that because this one doesn't have any factors, I can actually end up using the quadratic formula. So I have the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. As long as you know that this is the general form is ax squared plus bx plus c. Then you just plug in the values, right? Here, a equals 1, b equals positive 7, and c equals negative 64. We'll usually end up having something that we can factor and we can solve ourselves. But for this scenario, we'll use the quadratic formula. We plug stuff in. We have x equals negative b, which is negative positive 7, plus or minus the square root of b, which is 7 squared, minus 4 times a. A is 1, and c is negative 64. Divide all that times 2 times a. I'm using these values for A, B, and C. I do a little bit of simplifying, right? I get x equals -7 plus or minus the square root of 7 squared is 7 times 7, 49, minus 4 times 1 is 4, times -64 is 256, but minus the negative 256 will eventually turn into a positive, and we divide that by 2. So x equals -7 plus or minus the square root of 49 plus 256. And when you simplify a little bit, we get x equals -7 plus or minus the square root of 512. And everything's divided by 2. I forgot to put divided by 2 here. Now we're looking for a length, so I don't really want to leave it in radical form, so I'm just going to put that in the calculator. The square root of 512 is 22.6. So I know I have x equals -7 plus or minus 22.6 divided by 2. And then I have two versions of it. I have the plus -7 plus 22.6. Right? I split this into two parts. So the plus version of it is x equals -7 plus 22.6 divided by 2, and that gives us 4.3. One second. -7 plus 22.6 divided by 2. 7.8. So this is 7.8. As a length, I'm going to do the other one in red. So -7 minus 22.6, we get 29.6. Negative 29.6 divided by 2 is -14.8. Now, since we're looking for a length, this took a little longer than expected. Since we're solving for a length from these two values, we're looking for a positive length. So it's not going to be the negative solution, it'll be the positive one. When you cannot factor, right, the last scenario that we have is the quadratic formula, and that's this right here. If you look at this next scenario, hopefully this one is not as complex to solve and doesn't take us as long time, but we do very similar setup, right? We have the outside times the whole. The outside is x, the whole is all of it added together, x plus 4. We're adding them, and that'll equal the next scenario. The outside is 10 times the whole, which is also 10. This whole piece. So, in the inside we have x times x plus x is 2x plus 4 should equal 100. We distribute. X times 2x is 2x squared. X times 4 is positive 4x, and that should equal 100. I can move the 100 over because I have a quadratic of 2x squared plus 4x minus 100 equals 0. Since everything is an even number, I can divide everything by 2 to simplify this problem. And I'm going to work my way up here now. That gives me x squared plus 2x minus 50, and that equals 0. Now, I can already see that this one is also going to be a very similar problem as we did before with the Pythagorean, with the quadratic formula. I noticed that the a value here, a, b, and c, is going to be 1, 2, and negative 50. 2 times 25 is 50, right? I have several factors here that I'm working with. 2 times 25, I have 5 times 10, 50 times 1, but none of those will add up to 2, which means for this one to be solvable, I'm going to also resort back to the quadratic formula. I'm not going to go ahead and solve that, but I'm going to get 2 solutions from there, and I want to make sure I use the positive solution. If it's not factorable, we want to make sure that we can do the quadratic formula. So let's recap a little bit. As always, in the end, we want to be able to apply what we learned. This is a great moment to pause the video, try it yourself, work out the problems, and see how you're doing. What happens when the lines intersect on the inside? Right here I have them intersecting inside the circle. What happens when they intersect on the outside of the circle? And they're both secants. And what happens when they intersect on the outside, but one of them is a tangent, right? Feel free to pause it right now. I'm going to go ahead and solve these for you. For the first scenario, since they are multiplying, since they are crossing on the inside, I'm going to take a piece multiplied by the other piece. So x times x minus 9 will equal the other length times the other length. X plus 4 times x minus 12. Once it's set up, I can solve and I can factor. X times x is x squared. X times negative 9 is negative 9x. On the other side, I can do x times x is x squared. X times negative 12 is negative 12x. 4 times x is positive 4x. 4 times negative 12 is negative 48. And then I just combine a lot of like terms, right? X squared minus 9x equals x squared. These two can give me a negative 8x minus 48. Subtract x squared on both sides. These are going to nicely cancel out, leaving us with negative 9x equals negative 8x minus 48. Since there's no quadratic or no x squares, I don't have to worry about factoring anything. I just move everything to one side. So I'll move the 8x over. That leaves me with negative 1x equals negative 48. And when I divide both by a negative 1, I get x equals positive 48. I can plug this back inside if I wanted to find the length of any one of those segments, right? YO is 48. I can plug it into XO, OW, or OZ, and I can find all four lengths if I'm interested in that. For this next scenario, notice how they intersect on the outside. For this one, we want to make sure that we multiply the outside times the whole. I'll try to do a different color. Outside times the total. And that will equal the same thing as the outside here times the full length. That's our general formula for the outside. So for the next two scenarios, it's the outside times the whole and the outside times the whole. So that leaves me with the outside is 4 times the total, which is 4 plus 8. That's 12. That'll equal the other outside is 3 times the whole, which is 3 plus x, the full distance. Once it's set up, I can just multiply. 4 times 12 is 48. 3 times 3 is 9. 3 times x is positive 3x. Subtract the 9 on the other side. 3x equals 48. 48 minus 9 is 39. When I divide both by 3, I get x equals 13. And again, I can plug it in if I want to find different distances. But if x equals 13, the full length, A to E, would just be 16 if I wanted. Lastly, we have a secant and a tangent intersect on the outside. The outside piece times the whole length equals the outside piece, the 9, times the whole length, which happens to also be 9. Right? Outside times the whole equals outside times the whole. So let's see our setup. 5 times the whole, which is x plus 5, will equal the outside which is 9, times the whole length, which is also 9. Once it's set up, we multiply and we solve. 5 times x is 5x, 5 times 5 is 25, and 9 times 9 is 81. I isolate the variable, subtract 25 on both sides. 5x will equal 81 minus 25, which is 56. Divide both by 5. X equals 56 divided by 5, 11.2. And again, I can plug it in. I can find the full length from here to here. It's just 5 plus that, which would give us about 16.2. I hope this has helped. Again, the previous video was about finding angles, and this one is about finding lengths. The problems will look very similar, so you want to make sure you ground yourself in knowing, what am I looking for? The length of something or the angle of something? And that'll change the way we set up the problem. Please let me know if you have any questions. Hope you guys are having a great day, and as always, we'll calculate later.